All right. Hello, everybody, and welcome to the Chapter 6 walkthrough of the classical dynamics of particles. I got my tea here, and I hope everyone's ready to look into some methods in the calculus of variations. So, here we can see the chapter summary. We're going to have an introduction. We're going to kind of see what problem we're trying to solve, and then we're going to get into Euler's equation, another form of it, and then seeing how dependent variables play a role, and then get into some practice problems with that. So, without further ado, let's get into the introduction. Okay, so a lot of the problems we've seen so far in terms of Newtonian mechanics are going to be analyzed or a lot easier to do if you take into account Lagrange's equation, Hamiltonian's principle, and other problem-solving tips that might be useful, such as when solving, say, the equation of motion for a pendulum. When things get more complex, when you start to add in other moving parts. The point of this chapter, though, is to kind of touch on the theory of variations that affect classical systems, and we might kind of brush over some proofs. We might not dive too deeply into that. And as an example, they say a good example of the use of theory of variations is Fermat's principle, which from memory is like the principle of least time, which kind of says that light travels by the path that takes the least amount of time, which also happens to be like the shortest distance. And that's kind of how we get the ray vectors and stuff in optics. But anyways, let's move on to the statement of the problem, what we're really trying to learn in this chapter. Of the problem. Also, I kind of forgot to upload chapter 5 after recording it, so it's actually uploading right now as I am recording this one. So hopefully we'll have 2 new chapters uploaded on this channel today. And I got my first ever comments, and it was very cool to get a comment, on something I'm doing just for studying purposes. But anyways, okay. So the basic problem of the calculus of variations is to determine the function y of x such that the integral. So if I write this integral down, x1, x2, sum of function that depends on y of x, y prime of x. Okay. So let's post the picture, and let's get into what this is actually saying. Is we basically want to determine the function y of x such that this integral is at an extremum. This is the integral, so it's either at a minimum or maximum. So equation 6.1 is this equation right here. And this is basically letting us know that the y prime right here, this is just the first derivative, dy dx. And then the semicolon right here, oops, that's not the highlighter function, sorry about that. And the semicolon basically tells us that the independent variable x is separate from the dependent variable y of x and its derivative y prime of x. Now, the functional j depends on the function y of x, and then the limits of integration are fixed. So this basically tells us the function y of x is then to be varied until an extremum value of j is found. So j is the value of the extremum. Okay, and this means that if the function y equals y of x gives us, basically minimizes this integral, j, then any neighboring function, no matter how close to y of x, must make j increase. So if y minimizes j, if I have something that's very close to it, it has to make it increase because it's at a minimum. Okay. The definition of the neighboring function can be made as follows. So we can give all possible functions parametric representation. So y is equal to y of alpha x, and we can set alpha equal to 0, y equal to the starting value, plugging in alpha, which is just y of x, and this is our generic value. And then whenever we increase alpha, for j, we can set it equal to y of alpha of x is equal to y of 0 comma x, so our minimum value plus alpha and then some other function, where this function right here has a continuous first derivative that vanishes at the limits of integration here. Okay. Now, this situation is showed schematically in this diagram here. So let's try to look at it and see if we can understand it. So the function y of x is the path that makes the functional j an extremum. Okay, so here's our extremum right here. The highlighter's a little thick, so sorry about that. The neighboring functions y plus alpha, I don't remember what that Greek variable is called, whatever this is, unfortunately, vanishes at the endpoints and may be close to y of x. In other words, they start and end at the same spot. Right here, that's what it's saying. And notice that they're close to y of x, but they're not an extremum. And if we look at it, the length of this right here is greater, right? So the minimum path is y of x. Okay. Now, if we're allowed to vary our parameter with alpha, we can rewrite this equation in turn as follows, where j of alpha is probably as expected. You just replace the function of just y of x with y of alpha comma x, and then the first derivative, right, of alpha comma x again. Oop, I'm using the wrong pen. I was wondering why it was so light. Sorry about that. X dx, and this is basically a generalization of a function called a functional, which is an integral functional in this case. Okay. I guess this is equation 6.3. It's just a type replacement of the original equation up here when we include the parameter alpha. Okay, and now the condition that the integral has a stationary value, in other words, that an extremum exists, basically, occurs when the partial derivative of j with respect to alpha, when alpha is equal to 0, is equal to 0. For all, I guess I could write that. It's the for all symbol for math. For all of the other functions. Okay, so let's consider an example because I don't think that made too much sense. So let's consider a function f, which gives us a second derivative of y, where y of x is equal to x. So we just have a line. Add to the y of x function some variational parameter, sine of x, and then find j of alpha between the limits 0 and 2 pi. Show that the stationary value of j, the minimum, occurs when alpha is equal to 0. So let's look at a diagram for that. So we include alpha, which is the alpha sine x. So we have our line equation, right? And then we have our sine path. So if we were to look into it, we start with y is equal to, y of x is equal to x. So we have our line equation, and then we have y of alpha comma x when we vary it. So that's just x plus alpha sine x, because that's our function. Okay. So let's take the derivative of dy of alpha x dx. Well, take the derivative of this function right here. That's 1 plus alpha cosine x. Okay. Now, we know our function, right, is the function of the first derivative squared, dy of alpha x over dx squared. which is just equal to using like, a plus b squared. We have 1 squared plus 2 alpha cosine x plus alpha squared cosine squared x. And then we get our equation from 6.3 plugging into j of alpha. Integration limits x1 to x2 0 to 2 pi, because it asked us to do it from 0 to 2 pi, of 1 plus 2 alpha cosine x plus alpha squared cosine squared x dx. Now we can integrate that pretty readily. That's just an x, so I guess I'll just actually do the integral. So x plus 2 alpha sine x plus oh Jesus. Wow, my integration by hand is doing fantastic right now. Cosine squared x. What is the integral cosine squared x? Interesting. It's cosine 2x over 4 plus x over 2. Okay, so apparently it's alpha squared. Sine. These are just trig identities, I'm sure. But clearly I'm doing fantastic. 0 to 2 pi. And then if we simplify this, we should get from the textbook 2 pi plus alpha squared pi, which I can check right now. 2 pi right here is from there. Sine of 2 pi is 0, I think. 0, so that goes away. That goes away. 2 pi divided by 2, so that's plus. So we have an alpha squared. We have a 2 pi over 2. That's alpha squared pi. So that's what we get. Okay, so good. I can kind of do math by Googling what the integral of cosine squared is. But we get the same result as the textbook, and we get 2 pi plus a squared pi. So then we see that the value of basically j of alpha is always going to be greater than j of 0, no matter what we choose for alpha, right? Even if alpha is positive or negative, because alpha is squared here, and if alpha is 0, right, then this is minimized because you just get 2 pi. Okay, I think that's a cool example for why we care. And now let's get into the useful equation, Euler's equation. So 6.3 is Euler's equation, and this man has a lot of very useful equations and stuff in math, like Euler decomposition, writing your sines and cosines as complex exponentials, all that useful stuff. So let's do the derivative we were talking about over here for the condition to find that extremum. So is just the partial derivative with respect to alpha of this integral f, and I'll shorthand it as y prime, and these are all functions of x dx. And now, because the limits of integration are fixed, the differential operation only affects the integrand. In other words, we can bring this in. So therefore we have, this is equal to the integral from x1 to x2 of partial alpha plus prime y prime over del alpha, where all I basically did here is if you have like f of y and you want to take the derivative of that, that's just the derivative of, it's just chain rule. It's the derivative of this function times the inside plus the derivative of this function times the inside. So using chain rule, we get that, and then we can set dy d alpha equal to, or I guess partial is probably a more correct way of saying it, to the function. I really suck at writing that Greek letter, which I really wish I could remember what it's called, but sorry about that. And then the prime equal to the derivative of that. Oops. Dx. And then we can rewrite, that allows us to rewrite this equation as, oops, it's partial. Integral from x1 to x2 of plus with respect to the, ooh, this is not a partial dx because I think it's explicit differentiation. Okay. And now using what's it called, integration by parts, we can split this into two integrals, and for brevity's sake, I'm just going to screenshot the answer because my hand's already getting tired of writing, and I've been doing this for 5 minutes so far. And we can see that integration by parts leads us to this response, and remember, we have to bring the limits with us. And since this function right here is defined to be 0 at x1 and x2, if you guys remember from, not here, right? We can basically simplify this expression into this right here, which allows us to, we get rid of this basically, resolve this expression, which now seems to be independent of alpha, but that's not necessarily true because the functions y and y prime, remember, are still functions of alpha because they are y of alpha comma x, not y of x. Okay. So this lets us basically resolve it to Euler's equation, which then tells us that the middle of this integrand right here has to be 0 for alpha equal to 0, right? And if alpha 0, remember that's 0. So then we get f del y minus d minus the derivative with respect to x of del f del y prime is equal to 0. Okay, where y and y prime are the original functions independent of alpha because we set alpha equal to 0, so we got rid of this. And then this right here is known as Euler's equation. Okay, so that was a lot to unpack. So let's kind of look at an example to see how this really works. So let's do example 6.2, which says we can use the calculation of variations to solve a classical problem in the history of physics. The brachistochrone. I'm not entirely sure if I'm saying that correctly, but anyways, let's consider a particle moving in a constant force field starting at rest from some point x1, y1 to some lower point x2, y2. Find the path that allows the particle to accomplish the transit in the least possible time. Least possible time, we're minimizing the problem, right? Okay, so let's start with some coordinate system. So let's choose x1, y1. x1, y1 to be the origin for simplicity. And let the force field be directed in the positive x-axis, so this way. So let's just use their drawing actually, because it seems easier. And they use this as y and this as x for whatever reason, but it's the same thing regardless. And here we draw some random path, right, between the two, because we don't know which one minimizes it. Okay, now we know that if we ignore friction, right, the field is conservative, So that tells us that the kinetic energy plus the potential energy is equal to a constant value, right? Just a number. So if we measure the potential from x equal to 0, so if we have u of x equal to 0, and then if the particle starts from rest, that tells us that the potential energy u is equal to negative f of x, which is equal to negative mgx. I don't like that they use x. Why would they not just make this y like a normal two-dimensional problem? But whatever. Because of the force of gravity, and g is the acceleration imparted by the force. So using this to solve for t, right, we get v is equal to square root 2gx, since t is equal to 1/2 mv squared. And solving for the time for the particle to make a transit from the origin to x2, y2, so from here to here, that allows us to set up the integral from points x1, y1, x2, y2, distance, velocity, well, putting it in our actual units where ds is, that. We have dx squared plus dy squared to the 1/2, right? Since if this is a distance dy, this is a distance dx. To make the triangle right, it's Pythagoras. Okay, and then we have our equation for v, which is 2gx to the 1/2 from just normal energy conservation. And that allows us to rewrite our problem in terms of y prime. So let's set our integration bounds again. So we know x1 is equal to 0, x2, okay? And we're going to have 1 plus y prime dy dx, right? Squared over 2gx to the 1/2. Put everything under the square root with respect to dx, because the dx comes out. So we were basically just doing the integral over the x limits. And that allows us to basically identify a function f, which is right here, basically. So let's identify f as this 1 plus y prime squared over x to the 1/2. We're gonna ignore the 2g out because we can just take it out, right? It's just the constant numbers. And because we know that the derivative, the partial of f to y is equal to 0, Euler's equation becomes the derivative of d dx of just with respect to y. Partial of y prime has to be 0 since the first part of the equation is 0. And that then immediately then tells us that this right here has to be a constant with respect to x. So we can set del f del y prime equal to, they define it as 2a to the negative 1/2. We can just do this because this is just saying this is a constant, right? The derivative is equal to 0. Now, we can perform the differentiation of this. Oops, that was a weird arrow. But we can perform the differentiation, and we get y prime squared, or after squaring it, x1 plus y prime squared, which is just 1 over 2a from over here. And we squared both sides. That's why we got rid of the 1/2 over here. Okay. And then we can rewrite this as y is equal to the integral of x dx over 2ax minus x squared to the 1/2. Since we have y prime, remember y prime is equal to dy dx. So we solve for y basically. And now we can make a change of variable. So let's let x equal to a1 minus cosine theta dx is equal to a sine theta d theta. And don't worry if you're a little lost in the math, because if I didn't have the textbook in front of me right now, I probably would have not realized to do these substitutions myself. But then this allows us to realize then that like substituting these values in, we get y is equal to the integral of a 1 minus cosine theta d theta, which is a remarkably simple integral, right? So we get y is equal to a theta minus sine of theta plus, plus c. And writing this like parametrically, we have x is equal to a 1 minus cosine theta from above, and we have y is equal to a theta minus sine theta, which is probably a graphical thing you've heard before, a cycloid, which is the solution found, and then we just set the constant of integration to 0 for simplicity's sake. So the path then, as shown in this figure right here, what's it called? The constant a must be adjusted to allow the cycloid to pass a specific point. In other words, we have to change a such that we actually hit x2, y2. Okay. Right, because if we increase a, then all of a sudden we're like, making bigger ones. And if we solve the problem of the brachistochrone, it does indeed yield a path that the particle traverses in minimum time. But the procedures of variational calculus are designed only to produce an extremum. In other words, doing this will always give you a minimum or a maximum, and usually for dynamics, we almost always want to find a minimum. Okay. That was an interesting problem. Let's do... Yeah, we can do one more example, I think. Because I don't know how convinced I am about that one. I mean, I can follow the math. But, okay. Let's consider the surface generated by revolving a line connecting two fixed points, x1, y1, and x2, y2, about an axis coplanar with the 2 points. Find the equation of the line connecting the points such that the surface area generated by the revolution is minimum. So again, we're looking to minimize something. So let's see how we can do that. So I'll just screenshot the solution this time, because I think it's easier for me to just write and talk over this. The one I have to worry about copying it down. So let's assume the curve passes through both the points, right? And it's revolved about the y-axis. See, now we do x and y like this. I don't know why they did it the other way, but whatever. Let's calculate the total area of the surface of revolution. Or sorry, to calculate it right, we need to basically find the differential area element, dA. So let's look at this figure. So our dA, right, is equal to, so 2 pi r gives us the radius. So 2 pi x is our radius. And then ds is our integration variable, right? Where that's given by dx squared plus dy squared to the 1/2. Okay. So writing that gives us this expression. And then we can calculate the area just by taking the integral, right? And then taking that integral, we can set, let's just screenshot the rest of this, where again y prime is dy dx. So to find the extreme value, we can let f equal this again, similar to what it was before. It was last time it was 1 plus y prime squared over x to the 1/2. Now x is over here, but it's basically just, it's f dx, right? So if we insert it into equation 6.18, with respect to y is 0, right? Because there's a y prime here. But with respect to y prime, well, taking the derivative of this is just, because of chain rule, or I guess if you want to call it, I don't know, yeah, the multiplication rule, is x y prime over 1 plus y prime squared to the 1/2. And then remember, Euler's equation is del f del y plus del f, d dx of del f del y prime. So I have to take the derivative with respect to x of this is equal to 0. So that tells us this right here has to be a constant, and we're going to set that constant equal to just alpha. So then that lets us determine that y prime, right? Solving for y prime here, we get this expression, and then solving for y, because remember y prime is just dy dx. We just have a dy dx here. We bring the dx to the other side, so we have a dx there, and then we integrate it, right? Okay. And that lets us get this integral, which apparently has a solution of y is equal to, well, actually, yes, it does. I vaguely remember this integral, kind of. It's a Cauchy integral. Which I would not have known if I didn't see the answer, of course. X over a plus b. If I remember correctly, this integral is used. This is like a pretty common integral in physics. We see it a lot for whatever reason. And that lets us then know that x is equal to a cosh y minus b over a. Right? We bring the b to the other side, and we solve for x, and we get this expression for x, which is more easily recognized as the equation of a catenary, the curve of a flexible chord hanging freely between 2 points of support. What is a catenary? Let me Google that. Catenary. Very interesting. There's a whole Wikipedia article. Oh, it's one of these. Let me, in case you're as confused as I was, here's a picture off Wikipedia. That's a catenary. It's like what happens when, like, you know, like a rope has weight or whatever. Very interesting. Okay. It's not done, unfortunately. We just found our like equations, right? So we need to basically solve the original problem, right? Which is asking us to find the equation of the line that connects the 2 points, such that the surface area generated is a minimum when we like revolve it about the y-axis. So let's just, you know, oops, screenshot the wrong thing. Okay. Let's choose 2 points located at the points of interest, right? Joined by some arbitrary curve y of x. And we want to find y of x such that if we revolve the curve around the x-axis, the surface area of the revolution is a minimum. So we want a to be minimized. Okay. Well, remember dA was this and ds was that. So plugging in the equation for a, and we can set f again to this equation now. And then computing the derivatives of, which is just, you know, you get rid of the y for the df dy, and then for the y prime, it's just the derivative of this. Nets us these two values, and we're minimizing basically this surface area. Okay. So this allows us to rewrite the equation as ddx of that. And basically, it doesn't look very simple, right, to solve for y. Because we basically want to find y, or y of x, right, which is just y. Okay, so it doesn't seem very easy. You may have noticed this problem is just like an example 6.3. Okay, so this is basically telling us what would happen if we tried to solve it with y instead of x. Yeah. Whereas we already got our answer here before. So it should net us the same result, I think, is what they're saying. Okay. So that's it kind of for that example where we've kind of been getting used to Euler's equation, where just as a reminder, Euler's equation, oops, I wrote it wrong earlier. it was del f del y minus, I wrote a plus here instead, sorry about that, d dx of del f del y prime. This is just telling us that this is equal to this. That's the equation we're using. But we're always setting this equal to 0, so that's why I was confused. Sorry about that. But okay, let's get into kind of another form of Euler's equation. So 6.4, and it's in quotes because it's the same equation. Okay. And we can basically derive this equation from Euler's equation. So it's basically convenient in some cases to do so. But for functions that don't explicitly depend on x, in other words, where del f del x is equal to 0. And now we first note that for any functions f of y, y prime, x, when we take the derivative, when we take df, dx, sorry, those are not partials, that's just d dx of f of y, y prime, sorry, which is just, applying chain rule, del f, del y, del x, plus del f, del y prime, dy, sorry, these are d's, over dx, plus del f, del x, which we can simplify into y prime, or I guess just rewriting it, plus y double prime, del f, del y prime, plus del f, del x, basically getting rid of the non-partials, because remember, dy dx, that's just dy dx, and it's d dx of that, so that's just y double prime. We know, applying chain rule, basically, the derivative of this is y double prime plus y prime of d dx of del f del y prime, which we can substitute into this equation right here to get this expression right here, where the last two terms, in other words, these ones right here, can be written as, if I factor out a y prime, right, we get d dx of del f del y prime, this one right here, minus this right here, minus del f del y, which vanishes from the Euler equation, since del f del x minus d dx of f minus y prime del f del y prime is equal to 0. And this is the so-called second form of the expression. Now we can use this expression, or second form of the Euler case, in cases where f does not explicitly depend on x and the partial with respect to x is 0. So that then tells us then that f minus y prime del f del y prime equals constant, right? Because this right here has to be 0. Because we're told this is 0, right? That's what it means in this special form, because we're saying del f del x is equal to 0. So let's kind of look at an example for this. Okay, so let's look into what a interesting. I'm learning a lot of vocabulary today. A geodesic. I don't know if I'm saying that right, but it's a line that represents the shortest path between any 2 points when the path is restricted to a particular surface. Find the geodesic on a sphere. Okay, so the element of length on the surface of a sphere of radius rho is given by rho d theta squared plus sine squared theta d phi squared to the 1/2. Okay. And we can basically solve for s, right? Integrating. S is equal to rho between points, I'll call it 0.1 and 0.2 of d theta squared plus sine squared theta d phi to the 1/2. Actually, let's take the d phi out because it's squared, right? Okay. And now we look at this expression, and what do we notice? We have some value is equal to something, derivative of that, so we can let this equal f, right? So we let f equal to theta prime squared, or d theta, plus sine squared theta to the 1/2. And since del phi is equal to 0, since this doesn't depend on phi, right, explicitly, that lets us note that, this is a long one, so I'll screenshot it. We can basically set it equal to a constant now, right? Oops, wrong button. So let's just set this equal to a constant alpha from the second form of Euler's equation, and we can differentiate and multiply by f, and we get sine squared theta is equal to a theta prime squared plus sine squared theta to the 1/2, and we can solve for d phi d theta as d phi d theta is equal to a cosecant squared theta over 1 minus a squared cosecant squared theta to the 1/2. And solving for phi, bringing the d theta over here and integrating, we get phi is equal to sine inverse of cotangent of theta over beta plus alpha, where alpha, I'm just going to write that as a c actually, plus just some constant, and then beta squared is equal to 1 minus a squared over a squared. Basically, we don't want to write all these a's. Okay, and now we can rewrite this equation to solve for theta now, like how we rewrote it to solve for x in terms of y, and we get cotangent of theta is equal to beta sine phi minus c. And if we want to interpret this result, we can convert back to rectangular coordinates, which I'll just screenshot how they do it because it's a bit of work, but not really. Okay. To obtain unexpanding sine. Oh, this is just the trig identity of sine of difference of angles. By the way, here alpha was our c. They used alpha for whatever reason. I don't know. C is a better constant. I think I'm more used to as a constant of integration. And rewriting it, we basically get ay minus bx is equal to z, which where a and b are defined right here. These are all just constants, right? Because beta is a constant, sine alpha is a constant, cosine alpha is a constant. So it tells us it's just y minus x is equal to z, which is the equation of a plane passing through the center of the sphere, which basically tells us that the geodesic on a sphere is the path that the plane forms at the intersection. In other words, a great circle. Now, it's the maximum as well as the minimum straight line distance between 2 points on the surface of a sphere. In other words, if I have a sphere, I have 2 points, right? I can't really draw a sphere, but I don't know, bear with me. That's what it is. It's kind of like we intersected it with a plane and it's a circle, right? Okay. That's good for that example. It's the same equation. It's just a special case when we set del f del x equal to 0. But now let's look at functions with several dependent variables. I spelled with wrong. Several variables. Okay. Now, basically, we can rewrite this as, a fancier way is we just set f equal to f of the first pair, second pair, so forth, all with respect to x. Or if you want to write it more compactly, we can use indices. And then we basically have all the same equations. And then if we were to extend it, all we do is we just put in a sum, right? Since these are just basically summations, we can just put the sum in, and then we get the exact same expression we had before, this time just with indices. You're just basically summing each individual part in here. And then since the individual variations are all independent, it basically tells us then that we have to basically make it vanish separately for each of the expressions. In other words, we have I Euler equations, basically, for how many dependencies we have. So, okay. That's kind of what happens if we have a function that depends on multiple dependencies. But let's see what happens in 6.6, which is Euler's equations when auxiliary conditions are imposed. So let's say we wanted to find, as an example, the shortest path between 2 points on a surface, which we kind of already saw to do before. Then there means there has to be a condition that the path must satisfy the equation of that surface. Say, we can say something like g of yi with respect to x is equal to 0. Now, we saw this with the geodesic on the sphere, where the condition was g is equal to sum over I xi squared minus rho squared has to be 0. Okay, which basically tells us r is equal to rho is equal to constant, right? The radius of it's constant. But in a general case, we have to make explicit use of the auxiliary equation or equations. Now, these equations are called equations of constraint. Now, these are very important in general of constraint. It kind of tells you what system you're dealing with. So let's consider the case where f of some, if it lets me paste it, it does not, so I'll just write it. F is equal to f of yi, yi prime with respect to x is really just f of y prime, and then z prime with respect to x. And then we basically have our equation with just two things. Our sum turns into 2, right? We have, f1 and f2 basically, right? Or sorry. Yeah. Okay. And then that means we have an equation of constraint of the form g of, yi x is equal to g of y z is equal to 0. So the variations del y del alpha and del z del alpha are no longer independent. Okay, so that lets us tell us that they don't separately vanish at alpha equal to 0. So if we differentiate g from this equation here, we get dg is equal to basically just chain rule, right? Which is equal to 0. And then that basically lets us have now two equations with two different functions, variational functions, right? As we saw here. And then, therefore, by determining, the partial of y with alpha and the partial of z with alpha, and putting them back into the g equation, this one, the derivative equation, that lets us know that the partial of 1 with, it's kind of like, if you look at, if you take electrodynamics, like Maxwell's equations, you basically have an inverse relationship of the partials. And this happens because this term right here in general has to be 0. Or else it's a pretty trivial solution if del alpha is 0. Like dg del alpha is 0. Okay. So that lets us rewrite our equation up here as make it a little bigger, using these expressions here for del alpha, like del y del alpha, and for these ones, and del z del alpha. And then we can factor the expressions of, the variational equations. I really wish I knew what that Greek letter was. Let me go look it up. This is annoying me. List of Greek letters. Eta. Bro, that's been bothering me. Eta. Oh my god, that's been really bothering me. Okay. So factoring out eta 1 of x out of the square brackets and writing basically this equation, we can obtain this, right? And therefore, if we factor out eta 1 of x, right, from here, we get this expression here because we have n2 of x is equal to this times eta 1 of x. We factor it out. We have to put this in there. And then now that tells us we only have one arbitrary function, right? n1 of x. And you can do this for, n or I, whatever, eta functions. And therefore, we must have that this expression here has to equal this one. Let me see if I can understand that real quick. The expression in the brackets must vanish. So this right here must vanish in order for this, right, to have a minimum, because we want this to be 0. So that means this has to equal that, right? Why is it dg del y to the negative 1? I see. So what they did here was this expression right here has to equal 0. So I have this. Let me just highlight it. This is equal to purple, right? And then what they did was they brought this right here over to the other side, and that's where you get this, and then they left this one on this side. That's how you get that expression, which tells us that the left-hand side of the equation only involves derivatives f and g with respect to y and y prime, and then the right side has just the same thing, but with respect to z and z prime, right? And now, because of this, we can set them equal to functions of x, and we write that as negative lambda of x, as in like the two sides of this can equal some function of x, negative lambda of x, and this is also equal to negative lambda of x. And that lets us obtain two separate expressions, each with just, we have all y's here, and then we have all z's here. barring the x, which is what it's dependent on. And then now this lets us know that we can find the solution to a problem if we know y of x, z of x, and lambda of x, which basically allows us to set up the following set of equations where lambda of x is known as the Lagrange undetermined multiplier. Okay. So now this expression right here is equivalent to I differential equations, or I guess n differential equations yeah, I guess because I is your indice to it's the sum is 2n. N differential equations, which basically tells us that it's all basically the same math. It's just from the previous part, like 6.3 and 6.4. It's just extended. This is just what happens if you have to take multiple like equations of constraint into account. And then we'll see this used later on with like Lagrange and Hamiltonian like stuff. Okay, so let's do a practice problem because I know this has been confusing. I have definitely been confused. So let's see what happens if we consider a disk rolling without slipping on an inclined plane, and we want to determine the equation of constraint in terms of the coordinates y and theta. So y is, I would use that as x, but whatever. It's our distance basically, and that's just r theta, right? From, you know, basically like the circumference and stuff. Like that's just the way you go from linear to radial, angular coordinates, sorry. So the equation of constraint then tells us that the difference between these two is 0. And therefore that dg del y is equal to 1 and dg del theta is equal to negative r, right? From this equation right here. And then these are the quantities associated with lambda. So we're basically done actually. But we can also see this in integral form, which I'll just screenshot for brevity's sake, because I'm getting a bit tired. We can see here in integral form the general equation, and then it has an extremum, and that has to satisfy the boundary conditions when y of a is a and y of b is b. And then we have another functional, which is, we can see the analogy for a fixed value with a curve length of L. And then we can do the same stuff that we have done before, except we have a constant lambda such that y of x is the extremal solution of the functional. So then this curve y of x has to satisfy the differential equation, which this right here should remind you of the second form of Euler's equation. And apparently we'll work on the ditto problem in just a second. So, which basically is this problem. So let's go over that then, since it was mentioned. And there are proofs of all the stuff that's starred, by the way, in the textbook, but I will not be going over that for brevity's sake. So one version of the ditto problem is to find the curve y of x of length L bounded by the x-axis on the bottom that passes through the points negative a0 and a0 and encloses the largest area. The value of the endpoints A is determined by the problem. Okay, so let's look at diagram, what this is actually asking us to do. So we want to find the curve y of x that maximizes the area above this y is equal to 0 line consistent with a fixed perimeter length. So it has to go through negative a and a, and the differential area is dA is equal to y dx, and then the differential length along the curve is dl. This is kind of like how we had ds earlier. Okay, so we can use the equations we literally just made to solve this problem. So starting from j is equal to, let me just show you this equation, this one right here, is equal to, well, from negative a to a, we just have y of dx. And then we have our equations of constraint, which is y of x, y negative a is equal to 0, y of a is equal to 0, and then we have k is equal to the integral of dl, which is just L. So then the differential length, oops, I did the wrong button. The differential length along the curve, right? Borrowing from, our ds problem, it's the same math. It's just, it's just, dl. This right here is just, if you have a dx element, you have a dy element. That right there is dx dy. You just add the two, and it's Pythagoras, right? That's how you get a squared plus b squared equals c squared. Using that, we get basically the same f function, kind of, and we can plug that into our k value, which in this case is our g function because we're dealing with k, and our constraint functional becomes this, and we know it's equal to L, so that lets us then know that since y of x is just y and g of x is just 1 plus y prime squared, we can use the these functions in our previous equations, 6.78 right here, into this equation, because that's to satisfy that differential equation. And plugging in everything, we get this right here, 1 minus lambda ddx of y prime over 1 plus y prime squared to the 1/2 is equal to 0. So we can manipulate this equation, move this over, divide by lambda to get this expression, and then we can just simply integrate, right, to get this expression where we have just an integration constant, and then we can integrate again to get y, and then we can rewrite this as an equation which is just a circle of radius lambda. So therefore we see the maximum area is a semicircle bounded by the y is equal to 0 line. So the semicircle must go through points x, y at negative a0 and a0, which means the circle must be centered at the origin. And that's if we set both constants to 0, and then the radius is just a. In other words, which we probably could have guessed, to maximize the area, it's a circle from symmetry, or a semicircle. Okay. Let's quickly, and of course the length is pi times a, right? Or pi r. Because circumference is 2 pi r, so half of that's 2 pi. I mean, 2 pi r, so it's pi r, which is just pi a, because r is a. Okay, let's move on to the last section really quickly, which is just introduction to the delta notation. That's a terrible delta, sorry about that. Okay. This is just a way to write stuff shorthandedly so we don't have to keep writing all these. You can already tell I'm screenshotting a lot because I don't want to keep writing. So we can express this top expression as just delta j, and then we simplify this to delta y, where delta basically takes care of your partial, and it takes care of the dA over del A. Okay, where if that didn't really make sense, that's basically what it boils down to. So then that lets us rewrite the condition of the extremum, right, which is just delta j is equal to delta of the function. And then if we were to look at this in a figure, we see that delta y basically tells us our virtual displacement from the actual path. Okay. So moving from here, we can put it inside the integral, right? So we're moving it inside del f, del x, and then we see, again, chain rule. But we know that del y is, or delta y, sorry, is equal to delta of dy dx, which is just d dx of delta y, because these are linear operators, so you can interchange them. So that tells us that delta j is equal to this expression, and then if we were just to integrate the second term using integration by parts, which, remember, if you guys remember, we got some expression that had like x1, x2, and then we have this integral right here. This vanishes because it's 0 here and here by definition, because you have to start and end at the same spot as the original function. So we get this expression, and since this is what's it called? Like, since this delta y is arbitrary, the extremum condition, which is, we know, delta j is equal to 0, requires the integrand to vanish, which means this has to be 0. And what is this, you might ask? This is just Euler's equation, right? It's the same equation. So we can see that using just a different notation, we can kind of write it more compactly. So that's all for this chapter. There's a lot of not a lot of tangible stuff, I think, to wrap your head around, unfortunately. We'll be getting into some more physical examples, I think, in the next chapters when we get into like Lagrange and other stuff like that. But yeah, I hope you guys enjoyed it, and sorry if that was confusing, because it sure as hell was confusing for me. Okay. Yeah, without further ado, I guess, peace.